In this lesson, we're looking to review sketching exponentials. So we're looking at exponential graphs. Now, I'll start by just reminding you the shape. So an exponential, it can have four base shapes. Remember that the features are a horizontal asymptote, and it will either increase at an increasing rate, which will be an exponential growth, or we can have an exponential k where we will decrease at a decreasing rate. Okay. So if we let the asymptote for each of these be y is equal to 0, and we've got our x and y axis, the first base shape will be that. So that's when we're looking at y is equal to a to the power of x. So we'll pass through 1 there. When it's flipped upside down, then we're looking at y is equal to negative a to the power of x. When it's inverted about the y-axis, then we're looking at y is equal to a to the negative x. And when it's inverted in both axes, then we're looking at y is equal to negative a to the negative x. Okay, so that base shape is important. All exponentials will be limited by that asymptote. And generally when we're looking to sketch, we're focusing on being able to identify, obviously, the asymptote, the x-intercept, and the y-intercept. You may find an extra point in order to help you sketch the function. Okay, so if we look up here really quickly at the syllabus statements, it suggests that we need to recognize the graph in the form y equals a to the power of x, including the asymptotes, and then look at the translations where we have a to the power of x plus b and a to the power of x plus c. So that would be that vertical translation for the first one, and this would be a horizontal translation. Now, honestly, a horizontal translation is silly, and I'll show you an adjustment we can make to any exponential before we start sketching that will help you understand why this is the case. And then it also says, looking at the forms y is equal to b times a to the power of x. So we've got a vertical dilation, and y is equal to a to the power of kx. So again, ends up being a vertical dilation with that growth constant. Right. So if we put these all together, we've got y is equal to a to the power of x. Y is equal to a to the power of x plus d. Y is equal to b times a to the power of x. Y is equal to a to the power of x plus c. Y is equal to a to the power of kx. If we put this all into one form, and we've got y is equal to b times a to the power of kx plus c plus d, then we've got all those transformations in one. Now, I'm going to suggest that we only ever try to graph in the form y is equal to b times a to the power of x plus d, and I'll show you why. So if we go to manipulate this form, we have y is equal to b times a to the power of kx plus kc plus d, and that means we've now got b times a to the power of kx times a to the power of kc. Now, a, k, and c are all constants, along with b. So now we can write this all in front. We've got b and a to the power of kc multiplied by a to the power of kx plus d. Now, b a to the power of kc is just a constant. We can write this as a to the power of k to the power of x plus d, where we can relate that to the form where we just have that b value. We have a constant to the power of x plus d. So if we can manipulate it into this form, we can sketch any just using this approach. So we're going to jump into a few examples. You'll see it's pretty straightforward. The idea is if we can calculate the x-intercept, the y-intercept, identify the asymptote that's determined by d, and maybe find one extra point, then we can sketch any one of these functions without any issues. Okay, so we're going to look at these three examples. So example 1a, we have y is equal to 2 times 3 to the power of x. Now straight away, we don't have anything here, so it's considered as a plus 0. We can state our asymptote in a horizontal asymptote, so y is equal to 0. Nice and easy. So because there's a horizontal asymptote, and we can already start sketching x and y, horizontal asymptote is y equals 0, then obviously there can be no x-intercept, so we don't have to worry about that. So y-intercept is when x is equal to 0. So y is equal to 2 times 3 to the power of 0, which is 2 times 1 and 2. So the y-intercept is at 0, 2. So there we have our y-intercept. Now this is one of those scenarios where it would be helpful to find a secondary point. So let's say an extra point we'll look at when x is equal to 1. So we'll go f of 1 is equal to 2 times 3 to the power of 1. So 2 times 3 is 6. So we have the point 1, 6. So across 1 and up 6. And here is our exponential function. Not pretty, but a good indication of how easy these are to sketch. Now the second one, we have y is equal to 3 to the power of 2x. Again, we're looking at it as plus 0, so our asymptote will be y is equal to 0. So we can start to sketch again. So we got our asymptote y is equal to 0. If we manipulate this, it's the same as looking at y is equal to 3 squared x, which is 9 to the power of x. So there is no x-intercept, but for our y-intercept, when x is equal to 0, simply y is equal to 9 to the power of 0, which is 1. So our y-intercept is 0, 1. And then for our extra point, we'll look at f of 1 again. And so now we're looking at 9 to the power of 1, which is 9. So we've got the point 1, 9. So 1, 9. When we draw this out, we've got quite a steep exponential. There it is. Y is equal to 3 to the power of 2x. So nice and easy. Same approach with a little bit of manipulation. Now the third example is negative 3 to the power of 2x plus 4. In order to sketch this, we simply need to be able to look at the asymptote, and the asymptote is very obvious here. We've got a 4 here, a plus 4. So our asymptote is y is equal to 4. Now because the a value is negative, we're actually going to be existing below that, but we just have to find our x-intercept when y is equal to 0, and our y-intercept when x is equal to 0, and these points should allow us to sketch this quite accurately. So when x is equal to 0, we've got y is equal to negative 3 to the power of 2 times 0 plus 4, which is the same as saying we have negative 1 multiplied by 3 to the power of 0 plus 4, and therefore we have negative 1 plus 4, which is 3. So our y-intercept is 0, 3. When we look at the x-intercept, when y is equal to 0, we have 0 is equal to negative 3 to the power of 2x plus 4. When we add negative 3 to the power of 2x to both sides, we have 3 to the power of 2x is equal to 4. And by taking the log base 3 there, we have 2x is equal to log base 3 of 4. And x is equal to 1/2 of log base 3 of 4. So if we put that into our calculator, we get x is equal to 0.631. And so our x-intercept is 0.630. Now when we go to sketch this then, we start with our asymptote. And so we have an asymptote at y is equal to 4. We have a y-intercept at 0, 3. And we have an x-intercept at 0.63 and 0. Now when we sketch this out, that is what our exponential looks like. Y is equal to negative 3 to the power of 2x plus 4. Now if we want to check this on a graphics calculator, we go into Menu and Graph, and we type it straight in. So we have negative 3 to the power of 2x plus 4. So we draw this. We need to reset our window. There it is. So let's check it. G-solve y-intercept, which is f4, 0, 3, that's good. And G-solve root, which is our x-intercept, we've got 0.63, so that's good too. Now make sure that you've labeled x and y, and there is our sketch. Our final example is going to be a little bit more of a complex one. We can manipulate it, or we could work it out regardless. We're looking at sketching y is equal to 9 times 3 to the power of 2x, take 1, take 2. So start with our asymptote. Asymptote is at negative 2, so asymptote is y is equal to negative 2. So it's going to exist above that line, y is equal to negative 2. Our x-intercept is when y is equal to 0. So we've got 0 is equal to 9 times 3 to the power of 2x, take 1, take 2. So if we add 2 to both sides, we've got 2 is equal to 9 times 3 to the power of 2x, take 1. Divide by 9, we've got 2 on 9 is equal to 3 to the power of 2x, take 1. And when we take the log base 3 of both sides, we've got log base 3 of 2/9 is 2x, take 1. Add 1, divide by 2, and we've got x is log base 3, 2 on 9 plus 1 over 2. So x will be approximately negative 0.185. So we have an x-intercept at negative 0.180 and 0. And our y-intercept, when x is equal to 0, we've got y is equal to 9 times 3 to the power of 0, take 1, take 2. So y is equal to 9 multiplied by 3 to the negative 1, take 2, which is 9 over 3, take 2, which is 3, take 2, and is 1. So y-intercept is 1. When x is 0, y is 1. And now we can go about sketching this. So our asymptote, y is equal to negative 2. Our x-intercept is negative 0.18. And our y-intercept is 1. So here is our exponential equation. Looks like that. And it is y is equal to 9 times 3 to the power of 2x, take 1, take 2. Okay, so skill is relatively straightforward. When we get to algebraically rearranging to isolate for an unknown or numerically calculating, we have to be fluent. So that's an expectation. But you can see even with a complex scenario like example 2, it's still pretty straightforward. Thank you for listening.